Okay, we want to continue on covering chapter 16, which is all about mixtures.
Have you ever wondered how soap works? I mean, think about it. If your hands are dirty, grimy, and you run them under the faucet, have water pouring down on your hands, the water will wash and rinse some of the grime away, but really it doesn't do that great of a job cleaning your hands. But if you add a little bit of soap into the mix, suddenly your hands become cleaner much more thoroughly and much more quickly. So, what is it about soap that makes water so much better at cleaning grime off of your hands? In order to answer that, we first have to realize really what grime is. It's kind of a mixture of oil or grease with dirt. I mean, that's what grime is. And so, when your hands get dirty, the dirt mixes in with the oil and it clings to your hands. And so we want to be able to pull that grease and dirt off of your hands. Now, water, if you'll remember, is a polar molecule. It has a dipole built into it. And so there's a separation of the positive and negative charges that are available to attract other positive and negative charges. But the grime on your hand has segments that are mainly nonpolar. So the dipole of the water doesn't really affect it very well. What the soap does is it provides a bridge. Think of it this way. We know that water and oil don't play well together. If you try to mix some oil in with water, the oil's just going to float to the top and it's just going to sit on the top. They don't tend to want to play together. But what the soap does is it essentially connects the two together. What do I mean by that? Imagine you have some grime and you have some water molecules over here, and they don't want to play together. The soap molecule is actually a long molecule, and on one end is a polar region that can attract to the positive and negatives of the polar water molecule. And so they grab on together. On the other end is a nonpolar part that can attract to the nonpolar parts of the grime through the induced dipole attractions that we talked about in the last chapter. In other words, think of it like this. We have the water molecules over here, and they don't attract to the grime at all, but the soap has one end that attracts to water and one end that attracts to the grime. So when the water pours over your hands with the soap latches onto the grime and the water latches onto the soap, and as the water rinses off of your hands, it pulls the grime along with it. And that's why soaps and detergents are so useful for improving how well you can clean your hands using water. Without soap, you only have the mechanical action of the water hitting your hands. But with the soap, you actually make use of chemistry to pull the grime off of your hands and clean them. So we have here an image of some grime, a clump of grime, and there are these long molecules that are the soap molecules. Now the soap molecules have a nonpolar end that can attract to the grime, and it actually has an ionic bond at the other end which creates a polarization to attract the water molecules. So you can see this guy here, he's a water molecule, and here is the soap, and here's a water molecule. There is a attraction between the water molecule and the soap molecule. The other end of the soap molecule is attached to the grime. You have many soap molecules and water molecules that are able to grab a hold of the grime and pull it off like we talked about in the last slide. All right, so let's check our understanding. We have some grime, and it is attracted by the soap. How is that accomplished? One option is the dipole-dipole interactions. One is induced dipole. The other is hydrogen bonding, and then dipole-induced dipole. We know that with soap, you have a nonpolar end of the soap molecule attracted to the nonpolar grime,
and that means that you have induced dipole interaction.
The next topic we want to talk about is softening hard water. Now, you may have heard of these terms before, soft water and hard water, but have you ever stopped to think about what they mean? When we talk about hard water is water that has high concentrations of calcium and magnesium. In other words, there's calcium and magnesium dissolved in the water. And this creates undesirable effects because you can end up with the calcium and magnesium coming out of the water to clog up pipes. It reduces how well soaps and detergents work. It can leave behind soap scum. These are things that are not wanted most of the time, or really ever. And so that is why people want to soften hard water, because if the water coming into your house is very hard, it's harder to get yourself clean in the shower. It's harder to wash your dishes. And of course, it can lead to your pipes being clogged up. None of those are desirable things. We can talk about one of the big problems that having hard water can cause, and that is that it reduces the effectiveness of soaps and detergents. We talked previously about how soap molecules have a polar end and a nonpolar end, and that the polar end is attracted to the water and the nonpolar end is attracted to the grime. Well, when you have water that has these calcium 2 plus ions and these magnesium 2 plus ions, they actually get attracted to the polar end of the soap and interfere with its ability to attract to the water. And so that reduces the effectiveness of the soap that you're using to try to clean yourself, because not all of the soap is being used to do its job. And so what we can do is we can actually add other things into the detergent that attract those ions more strongly than the soap molecules attract them. And they bind them up so that they can't interfere with the action of the soap. One of the common additives that is added to soften water is sodium carbonate, which is Na2CO3. And so here we see the two Na atoms and then the C and the O3 here. This is the chemical compound Na2CO3, sodium carbonate. And so what you can see happens is this guy actually separates out, and this calcium 2 plus ion bonds here, or this magnesium 2 ion bonds there, and in either case you can form calcium carbonate or magnesium carbonate. But the point is that these calcium ions and these magnesium ions get bound to these additives so they can no longer interfere with the action of the soap, because they're more strongly attracted to these carbonate ions than they are to the soap. Now, if you have really hard water in your house, rather than having additives into all your soaps and detergents, one of the things that you can do is actually have a water softening unit where the water comes into your house. In these kind of units, water is passed through a large tank of water that's filled with these tiny insoluble beads that are made out of something called an ion exchange resin. The surface of the resin contains many negatively charged ions that are bound to positively charged sodium ions. And so as the calcium and magnesium that are dissolved in the water, as those ions pass around and over that resin, the ions displace the sodium ions and therefore become attached or bound to the resin. The calcium and magnesium ions can do this because they have a 2 plus positive charge, which is greater than the 1 plus positive charge of the sodium ions. In other words, those magnesium ions and calcium ions, they're more attracted to those beads than they are to the water, so the beads pull them out of the water. In this way, the resin exchanges ions. The sodium ions are being exchanged for the calcium and magnesium ions. Eventually, though, it all gets used up and you have to replace the resin or sort of recharge it. And the way that you can recharge it is actually by flushing it with a concentrated solution of sodium chloride. And so that sort of replaces those sodium ions and lets you start the whole process all over again. In this next slide, we want to talk about purifying the water that we drink and use for other things like bathing or washing our dishes and whatnot. If you have polluted water or water that has some kind of impurities in it, it may not be safe to consume. It may poison you. And so we want to see how it's possible to take water that's not safe to drink and remove the things from it that are poisonous or things that can cause problems. And so this process is called purification. So let's take, for example, the case of purifying seawater. Now, as you know, fresh water doesn't have salt and seawater does. Seawater has all these salts in it that make it unsafe for humans to drink. So if you live in a desert, someplace where there is not a lot of drinkable water, you need to be able to, for example, if you live near the ocean, you could take water from the ocean and remove the salt, remove the impurities, and then have perfectly usable drinking water left over. How do we do that? Well, this process is called desalinization. Sal is from salt, and so we're basically desalinization means removing the salt, the process of removing salt. And there are generally two different approaches to this. One of them is called distillation, and the other is called reverse osmosis. So one of the easy ways to think about distillation is a very common cheap technique for creating drinkable water is through the process of distillation. Now here we see an image of something that's called a solar still, and the idea is this. So you have a water that is salt water, or for some reason it's maybe not as pure as you want it to be, and so you have this transparent membrane here, and the sunlight shines through and it warms up the water to evaporate it. And so as the water vapor rises, it sort of condenses on this piece of glass here, and these beads of water then drip down into this well. Now let's say in here you've got salt and water mixed together. Well, water has a boiling point of about 100 degrees Celsius. It's 100 degrees Celsius. And salt, on the other hand, sodium chloride, it has a boiling point of about 800 degrees Celsius. And so the salt is not going to be given enough energy to come up into a vapor and cling in the same fashion. So the water will be separated first, and it'll leave the salt behind. And so the water coalesces and condenses on this glass plate, and then it drips down, it slides down under gravity where it is collected in this well here. You could do the same thing if you had some container of water that you could have over here. And if you have your container here, you could actually apply some fire underneath to boil the water, and then the water would rise through the tube, and then you could bring it over here and condense it, and the impure parts would still be left behind because they boil at a much higher temperature than the water, so the water is able to be separated from those constituent parts. So this is a process called distillation. Now, the other technique for purifying water is what's called reverse osmosis. And in order to understand reverse osmosis, you must first understand regular osmosis, which is simply called osmosis. And so we can see an image here depicting, we have a couple of different regions here that are partitioned by this semi-permeable membrane that you can see right here. Now, this membrane has holes in it. And the reason it's called semi-permeable is that these holes are big enough to let the water through, but not so big as to let the other stuff that's dissolved in the water through. And so the water basically what happens is when you have this semi-permeable membrane, over here, the water is going to pile up on this side at a higher concentration than the water on this side because these big molecules are sort of displacing some of the water. So there's fewer water molecules piled up on this side than there are on this side. And so since the concentration is higher, some of these water molecules are going to slip through the membrane. And so you'll have fresh water basically moving into the solution and diluting the solution. That's osmosis. It's this flow of water across a membrane because of a difference in concentration. Now, what reverse osmosis is, imagine in this container, imagine you had a piston and you pushed on the water this way. So here we have the side of the water that's got the impurities in it, but you're pushing it. And so naturally what would happen without the piston is the fresh water is going to flow into the concentrated side. But when you press from this side over that way, the water is going to flow in the reverse direction because you've created an excess in pressure. That excess in pressure is going to push the water molecules to the pure water side. Now, these big molecules, of course, can't get through the holes. And so what you're basically going to do is you're going to leave the salt or whatever other contaminants you have, they'll be left behind, but this other water will be squeezed through. And I've made my picture kind of messy, but I hope you get the idea that we're essentially using the process of osmosis, but we're forcing it to go in the wrong direction so that we leave behind the contaminants and push all the pure water into the other side. And so if I've got salt water, I can separate the salt from the water and be left with water that I can actually drink or use for whatever reason. So here we can see this sort of illustrated in a more clear diagram. We have two regions. We've got one that is containing fresh water and one containing salt water with this semi-permeable membrane. Now, if we just leave it set up like this, what's going to happen is the fresh water is going to come and flow into the saltwater portion, and that means this guy is going to go up and it will continue until it reaches an equilibrium where there's imbalance. You can see this guy has gone down a little bit and this guy has gone up a little bit in this middle picture. Now, what you can do is you can apply an external pressure, this piston here, and push the water back through the filter, leaving the contaminants on this side and giving you more fresh water on that side. Now, we can also apply some of these ideas for the treatment of wastewater. And so the water that flows into the sewers, we can clean and purify that as well. But this is a little bit more tricky than desalinization, which is just simply removing salt from seawater. In this process, first of all, you have some screening, some like physical mesh screens that remove large insoluble items from the water. And then we have a primary treatment that allows smaller insoluble items to sort of settle to the bottom or rise to the top, depending on whether they're more dense than the water or less dense than the water. If you let them just sit there, the ones that are less dense will rise to the top and you can scoop them off. The ones that are more dense will sink to the bottom and you can separate them that way. The secondary treatment aerates the water. That means it dissolves air in the water, and this process allows finer particles to also settle for removal. And then the tertiary treatment is actually where we filter the water like we've seen in the previous slides. So here we can see this sort of a treatment depiction of all this process. So we have the different stages of wastewater purification. And also it's worth noting that very often these things are treated with chlorine, which is something that can kill bacteria to make it more safe. Now, chlorine is used a lot of times, and it has a nice effect that it actually will stay in the water for a longer time, and it will continue to kill the bacteria. In Europe, they actually prefer using ozone compared to chlorine. In the United States, we tend to use chlorine for this process, but In Europe, a lot of their purification treatment plants use ozone. Now, ozone has an advantage over chlorine in that it can also kill viruses, not just kill bacteria, but kill viruses too. The disadvantage of ozone, though, is it's kind of one and done. Once you've passed it through the water to kill the viruses and the bacteria, when it goes on, it's no longer offering protection. So chlorine has the advantage that it will continue to disinfect the water for some time later, whereas the ozone will not. And so hopefully that will help you understand a little bit better how this process works.